So a little background. So what we're doing is we're in the process of creating an entire tracking model for exascale programs around the world. And when I say exascale, Bob's going to be presenting more of the kind of hardware system view. That's kind of the first piece of it. We're looking for all the different software investments, new core technologies, whether it's in compilers and storage, interconnects, but we're looking at the whole infrastructure, including power and cooling. What our objective is to actually create this whole framework where every quarter we track each one of the projects around the world, who are the key researchers to help them make collaborations, what their goals and objectives are, and progress to date. And we'll be making this public to everyone so everyone can kind of see who's doing what. And what we're hoping to do with this is to help optimize the exascale development around the world. So there isn't duplication of efforts, and also so people can understand what everyone else is doing. And what Bob's going to be showing is kind of the first nugget of this whole data structure that we're putting together. So with that as an introduction.
Great, thanks, Earl. Hi, how's everybody doing today? The point here is, this is an ongoing study at this point, which is spectacular. Last year, Riken from Japan asked us to put together a study that said, can you give us kind of a snapshot of what's going on in exascale? And they have asked us to continue that work. So this is an ongoing effort, and what's really nice about it is we are adding data on, and sometimes it seems almost like a daily basis. So if you see your favorite exascale system up here and there's some information you have, please let us know. If you don't see your favorite exascale system up here, please drop me an email and say, what just happened here? Why aren't you adding this as well? So as I said, this is an ongoing activity and one that we are updating on nearly a continual basis. Fundamentally, the project requirements was simply gather information on pre-exascale and exascale systems today through 2028. And you'll see why we picked 2028. There's plans made by organizations to actually think out that far. Nothing terribly concrete except the delivery date. The mandate was to concentrate on major HPC developer countries, certainly the US, China, the EU, Japan, and perhaps others if there is activity that we see that comes up going forward. The key here was to build a database of technical information on the research and development efforts of these next generation machines. And I'll get into a little bit about some of the specifications that we're trying to collect. And it's not just simply a litany of what processor base, what size memory. That we're trying to push the envelope a little bit more. And in some sense, capture the essence of what the mood or the theme or the motif of exascale development really is, as opposed to just simply looking at hardware specifications. And one of the most important things for when you deal with big systems like this, it's trying to understand the information, the flow of funding. Particular areas of interest are how much NRE is being included in a system. What does it take to actually put a system on the floor, whether you're buying it from a vendor just by, for lack of a better term, going through the catalog and saying we want one of these, to the other extreme, which is basically working hand in glove with a number of technology development firms to really craft a system that contains a significant amount of NRE hardware technology, software capabilities and such. So really try to understand the confluence of forces that have to come into play to ultimately get a machine on the floor. We are, as I said, we're trying to collect as much data as we can, and there's the usual suspects up there. We're looking at plan performance, architecture and node design, power, failure rates, and something that we're calling key performance indicators. And here we're collecting again the usual suspects: theoretical peak, LINPACK performance, but also we're trying to delve a little more deeply into really what the people that are designing and trying to eventually plan to use these machines, what they really run out of this. And it's probably not a surprise to this group, but fundamentally no one's talking about exascale in terms of theoretical peak performance anymore. We're not even seeing an emphasis on what you would consider to be kind of standard benchmarks, something like LINPACK. What we're seeing now is more a degree of sophistication that says what we really want is we want to be able to provide sustained performance on our key applications that meet these specific requirements. And in many cases, it's simply an upgrade. We're looking for 20 or 50x off our existing system. So there's a lot more attention being paid right now to, I think, the use of the system, how valuable it would be to the researchers using it, as opposed to just simply saying, we have a system that can do 10 to the 18th floating point operations per second, and be proud of that. And in fact, if I can just digress for a second here, the exascale race as it stands right now, I think we need to stop calling it a race, because what's happening is in my mind, it's mutating more into a series of events. Call it an exascale decathlon, in the sense that we now have so many different flavors of what exascale really is. And the first exascale machine, and maybe you heard it here first, but this is Bob's prediction, is that the first exascale system out there will be what we've started to hear out in the sector as being called AI exaflops, which means we're doing 8-bit precision running on a lot of GPUs, and that's going to be kind of an exascale system on itself, kind of AI deep learning. Then we're going to have basically embarrassingly parallel exascale, where you have a large data center with lots and lots of systems running that can run an embarrassingly parallel benchmark to say this is an exascale system. It may never run as an integrated exascale machine again, but it'll be in a big data center, last long enough to justify being called an exascale system. We're going to have big data machines that aren't so heavily dependent on computational flops, but are looking at other kinds of applications. That is another brand of exascale. And finally, the one that perhaps most in this room are most familiar with, which is computational modeling and simulation, the traditional exascale systems. Those are at least 4 different kinds of exascale systems, and I think we really need to be cognizant of what each machine is capable of and what it's targeted for, because at least in the early days there's going to be some specialized architectures for each of those kind of systems. So really look for the kind of where in the decathlon this particular machine is trying to optimize itself. One of the other things in key performance indicators that we're noticing when we look at this is that utilization, the idea of how much of your machine is being tapped into computationally, is something that's not being nearly as gauged as critical as in the past. We've already talked about the fact that as Moore's law pushes the ability to put more cores on a chip at a relatively decreasing price, cores become essentially free. And I think we're starting to see an understanding that there are other things that matter when you're looking at the overall performance of a computer, and simply keeping the CPUs busy, the adds and the multiplies running, is not something that we're seeing as a requirement anymore. I don't think sysops are going to get in trouble anymore if they're not running their machines at 90% utilization. That doesn't seem to be a factor. We'll talk a little bit about power, because there's some interesting surprises going on right now in how people are thinking about powering up their systems. We're going to talk a little bit about prices, and here the numbers are all over the place. Again, what's most interesting to me about looking at prices is people are looking at prices as a time over money concept. The idea that, yes, I can get an exascale system in year X, but if I wait X plus 2 or X plus 3, I can get 3 times the compute power or 3 more systems at the same price. So there's a lot of expectations that the first exascale systems, you're going to pay dearly to be a trailblazer here, and that if you can wait a few years, you save in hardware cost, and interesting, as I said, we'll get to in a minute, power cost. There's an expectation that power will be a very good price performer if you're willing to wait 1 or 2 years, to not be at the front of the race. We're also looking at a number of ease of use features. The idea is when you drop an exascale system off into a facility, how amenable is that system towards development of new interesting software, the porting of code. As Earl mentioned earlier, we are somewhat surprised that there's not a lot of rewrites, complete rewrites of software. It seems to be the general trend is we're going to take what we have and make it work on this system. So the issue of looking at software porting as opposed to development is also something that we think is going to be very important going forward. Certainly we will cover all the interesting hardware attributes and some of the software stuff. The key one I just want to point out here is in the other software. We're looking at some of the more newer developments in software going on, and the first one, of course, would be folks bringing in deep learning software into their HPC environment. We're looking at the use of containers and other forms of virtualization, and also the ability for these systems to become more amenable towards, as Earl talked about earlier, the idea of moving data of workloads back and forth between your on-prem system and your HPC in the cloud. The idea that people will be increasingly writing programs that can migrate between the two with a minimum pain level. So we're trying to keep track of what's going on in terms of non-traditional software, at least software that 5 years or 10 years ago wouldn't have even been considered to be part of the suite of software that you'd expect to see on a big machine. And as we said earlier, we're looking at R&D plans and we're looking at partnerships. The general trend today seems to be these are big systems and no one can really go it alone anymore. And so we're seeing lots and lots of collaborative activities between government and industry, between certain government organizations and the industrial sector. It's much more confusing web of development than it was perhaps even 5 years ago, where it was pretty much a straight line between a research facility, a couple vendors at most, and ultimately machine at the end. So we're trying to figure out a lot of the networks that go into that. So at this point, we can look at the computers that we're talking about in the study today. And the ones that are kind of the historical reference, they're the ones that have been introduced in the last few years. And we're keeping them in the database just so people can do a certain amount of trend analysis. And as I said, we've already got, NERSC 11 knows that in 2028 there's going to be a system in Lawrence Berkeley Lab that meets their requirements. That's about all they know right now. But this is basically the list. And as you can see, it's heavily populated with lots of Department of Energy systems, both within the Office of Science and the NNSA world. We've got a number of Chinese pre-exascale prototypes that they're looking for to bring out in 2019 and earlier, and then some of their bigger systems in the 2020 timeframe. There were some European activities going on here as well. But as I said, we're adding to this list as the data comes in, and hopefully we'll grow this as time progresses. This is just basically some snapshots of what's in the database, and it basically shows what we're looking at, who's going where, just more information as it becomes available. And ultimately, this is basically one segment of the actual Excel spreadsheet, which is growing in leaps and bounds as we get more information as it comes in. Basically, what I wanted to do is more or less give you a sense of if you guys had a couple hours or a couple days, or for some of you a couple minutes to look at the existing database, what are some of the insights that perhaps you'd come away with? And so I thought I'd just throw up some of the things that really jump out at us at Hyperion when we look at that, where the exascale world is going at this particular point. And really, no surprise to anyone, what we see are major HPC suppliers in regions including China, EU, Japan, and the United States are all looking at exascale development. Most of the systems that we see right now are pre-exascale designs, systems that will underwrite the technology critical to the big exascale machines we expect to see in 2020 to 2022. And I think that's a key point, is if you remember back to the hysteria of perhaps even recently as 3 or 4 years ago, there was a sense that the world was going to have to change, that we were going to have to rewrite everything in hardware and everything in software to get to exascale, and it was going to require a paradigm shift. And really what we've seen in some senses is an evolutionary change. There's new technology being injected into exascale designs, but it's really, I don't want to say at the margins, but there's no great watershed event or tectonic shift in the way some of these big systems are designed. And perhaps more importantly, what it means is that the prototype systems that we expect to see in the next few years will be, in some sense, accurate representations of the exascale systems that will be rolling out in 2020 and beyond. There's not going to be any huge surprises. It's more about it's not can we make exascale, it's basically who's going to pay for exascale at this point. The technology is generally in place. As I said, the bulk of the systems in the next few years, basically 10 to 300 teraflops, and moving outward, it's following the kind of standard curve that you expect to see when you look at the top 500 list. There's certainly many architectures under development. I said that the technology is all in place, but everyone is playing with their own particular version of what exascale means. And again, this goes back to the decathlon concept. It's what you really want out of the system. That said, what we're seeing now is a general sense of, I think, innovation, the kind of innovation we haven't seen in the HPC sector in a long time. There's a lot more activity going on in folks saying, okay, we're going to build our own system. We're going to go out and find our own processors. We're going to put together our own interconnects. It's much more of a kind of a free-flowing activity, because the parts, the sub-assemblies, the critical subcomponent technologies are available, and you can basically mix and match to figure out exactly what kind of system is going to meet your workload. In addition to that, we're also seeing, and certainly I think the Department of Energy is taking a leading role in doing interesting NRE work in terms of developing some of the technologies that they want for their systems. And this brings back the interesting question in terms of, is this the kind of technology that can help the HPC sector writ large, or is it something that may be specific to just DOE requirements? And that's an interesting question, and something I think we're gonna keep an eye on as time progresses. Earlier, by the way, I'm also the timekeeper for the group, so the speakers are going to be glaring at me, and I made the wonderful mistake of not starting the clock when I started to talk, so that was purely accidental. I accept no blame there, so I'll keep an eye on the clock. Power consumption turns out to be a major issue here. And again, we go back to 5 years where people were talking about where we're going to get 75 megawatt capabilities. We're going to have to start locating these things near nuclear power plants and such. That particular fear doesn't seem to have really reared its ugly head. And we're seeing that basically everyone is pretty sanguine with the concept that they'll be at 30 megawatts and below. That's certainly a manageable concept for exascale as it's planned today. And we're in the process right now of really gathering, zeroing in, kind of drilling down on some of the important power and cooling data and insights from HPC centers, not only in the US, but around the world, government, commercial, and even academic. And I could just give you a flavor of some of the things we're seeing so far. The folks we've talked to basically said, you're looking to pay about $1 million per megawatt per year for a system. That will probably be around 25 megawatts. Now, there is a huge caveat to all that, and I'll show you in the next chart what the huge caveat really is, because this number can significantly vary. And when you talk to folks without some of the interesting backgrounds about what they pay for electricity, it doesn't seem to make sense. But when you start to see the variation of electrical costs around the world for power, certain things do start to click in. All of them, of course, are seeking PUEs of less than 1.1. That seems to be a very, that's almost a given at this point. And in fact, to the point where I think we're going to have to start to reevaluate what PUE is, because the numbers are going to become vanishingly small. What's interesting, though, is that some of the general failings about PUE is they fail to really understand or appreciate what's going on outside the facility in terms of power cost and cooling cost. And some of the folks I talked to who are absolutely giddy about their PUEs are in places where it's generally colder in the winter. Yes?
PUE is a TLA, I don't know.
Oh, I'm sorry. It's basically, I'm sorry, I should have explained that. What PUE is, power utilization, it basically talks about the fact that if I've got a facility that has a computer in it, how much of the power going into that facility is used by the computer versus how much of it is used by the facility. So if you have additional power, UPS requirements, battery backups, the cooling regime, that counts to the power going in, but not to the computer. In fact, so the bottom line is if you've got a system that's sitting in a very cold place, you can cool that system much more effectively than if you're sitting in, say, Albuquerque, yeah. And so those numbers are somewhat suspect at this point, and I think that the sector is due for a certain kind of revamp. The other thing is that PUE doesn't talk about how much power the computer is using, because it just assumes that the computer has a peak power performance. But if you're never running at peak power utilization, your realistic PUE actually starts to change because the computer isn't consuming as much power as you thought it was. And this is another interesting point about power that we're running into. One needs to be very careful when one talks about peak power performance of a system. And what we're starting to see now is the realization that peak power perhaps is a measurement of how much electricity you can deliver to the computing center floor. I don't see that being as popular anymore. Now, what we're seeing is peak power is being defined as the power that your computer uses when you're running LinPack, which means this is the most power this machine will ever be sucking up out of the wall, because you can't get much higher utilization than that. And so when people talk about sustained power, they're talking about understanding how much power the system uses when it's running its typical workloads. And that can actually be significantly below LinPack peak power and certainly below wall power. So folks are trying to cut this a little more finely in terms of trying to figure out exactly what they mean when they talk about how much power I need in this building, because those numbers can significantly affect your operating costs. We talked a little bit about one-time installation cost, and basically here we run into cases where people say if we have to build a greenfield building for an exascale system, we're talking a lot of money for power and cooling to set up the capability. A lot of folks are quite happy that they can put them in existing facilities. We're not seeing, as I said 5 years ago, the requirement to build new buildings to field exascale systems. It's much more of a we can upgrade and save some money. So this is the chart I alluded to. And it literally talks about the variation in how much different countries, and this is an overall average. So I wouldn't look at the absolute numbers, but to me, I think some of the relevant numbers are particularly enlightening. Basically, if we ascribe China and India to having a unity power cost, the U.S. is about 50% more, France a little bit higher, and Germany. The bottom line is here, you never ever want to put an HPC in Denmark. You're just going to pay huge amounts of money to put that system there. And what was interesting is I talked to a lot of data center folks, and I said, okay, you're a potentially big power user. What are you going to get if you go to your utilities and say, hey, can we cut a deal here? We're a big power user, reliable. And most of them said no, they don't get much. They're paying basically what any large kind of power user would use. So the numbers that you get from an average perspective are I think, pretty good. I think if you go down to Oak Ridge, they seem to have a little in with the Tennessee Valley Association, and they're particularly proud of their energy cost. But in most cases, these guys are not sitting down with the power companies and getting great deals. As I said before, most aren't focused on peak performance anymore. They're looking at some more sophisticated metrics and really about end-to-end. Steve, you give me a look. Should I start wrapping up here? Okay. He always tells me to speed up. Okay. There's a wide mix in exascale budgets. Some of them goes high as $250 million with lots of NRE on the other end. That I think as I said before, when you look at the kind of system that basically sits on the floor, trying to figure out how much NRE actually went into that machine is going to be increasingly complicated because there are just so many more players involved in getting that system located there. And really we're looking at some other folks who are just basically saying we're going to wait 2 years after the first ones come out and really just look to see what's commercially available and buy big systems from that way. So the budgets can vary in some cases by an order of magnitude simply as a function of time. There's certainly lots of hardware trends going on out there. As I said, there's in my mind almost a reemergence in processor vitality. We've got Intel, we've got Power, we've got ARM, we've got some custom processors coming out of China. There's lots of experimental architectures going out there, and I think it's a really exciting time to be looking at computer architecture simply because the variety and the ability of some places to actually take risk and go out, risk, no pun intended there, and go out and actually deal with new processors on a relatively expensive machine. We're seeing, as I said, to my mind, the architecture seems to be relatively stable, but what's going into the architecture, things like burst buffers and solid-state storage and smart interconnects are basically taking that architecture and making it much more sophisticated / complicated. Writing code to optimize when you've got a smart interconnect and storage buffers and lots and lots of options for how you arrange the programming means that it's going to be really hard to actually optimize some of these systems in the future. That's why we kind of put in the ease of use features just to deal with some of that stuff. InfiniBand, OmniPath seem to be the choice in most cases, or custom. We're seeing a few customs, and certainly storage. Storage is going to eat everybody's budgets big time. Lots of requirements there for both scratch and something a term I've come familiar with recently called campaign storage. The idea that there's certain amounts of large data that you may need to do a project. If you're designing a car, I only need this data available for 6 months, but I need it available fast, and then I can roll it out. And so we're going to see, I think, a little more sophistication in the storage hierarchy, which means that data shepherding, making sure the data you need is at the level of access and density that you need it at to do your job that day. Someone's got to come in the night before. Pixar does this. They make sure that whatever cell someone's working at, there's a professional who says, okay, I'm pushing the data out from here to here so it's available the next day. I think that's going to become an interesting problem. We're seeing some new software trends. Linux is Linux. It's not going away. Everyone basically goes there. Lustre and GPFS are going to be the file systems of choice, as I said earlier, but there are some non-traditional HPC software out there we're keeping an eye on in terms of big data infrastructures, virtualization schemes, Docker, and of course, the soon-to-be 800-pound gorilla in the room, deep learning. That is going to, I think, change the way software is running on some of these systems. It has different and unique requirements, and we're going to start to see originally deep learning being driven into traditional HPC architectures. We're going to see some special purpose deep learning appliances coming out there that are going to change some of the requirements. That's where we stand right now. Okay, and the bottom line here is if you want to access the full exascale report that we completed last year for RECON, you can go to this address and download it. And as I said, though, that was really just a snapshot where we kind of hit a t equals 0 and hit the print key. But as I said earlier, this is an ongoing project and something that we want to continually update, and hopefully we'll be able to roll out updates as they become available on almost a daily basis.
Only 15 minutes over.
No, it wasn't that bad, was it?
Okay. We can take maybe 1 or 2 questions. And go ahead, Vince.
Have you seen anything of non-volatile memory? Is that showing up anywhere?
You mean solid-state disk kind of stuff or NV?
Volatile memory, not storage.
Certainly, I mean, everyone's looking at flash as a way to do business.
The actual memory not losing its...
Yes.
Yeah.
When you turn the power off.
Yes.
It has tremendous software implications.
It definitely does, and what's interesting, the price is coming down on that. The price has come down, and so in some cases it's bridging the gap between volatile memory and disk.
Have you seen any of that showing up in HPC?
Yes. There's a huge effort to really to push non-volatile into the hierarchy between basically traditional volatile, DRAM and spinning disk and solid state disk. So yeah, it's there's some issues with it, but it's very attractive at this point.
Yes.
Do you have a sense of the percent for NRE, what the percentage is for NRE? Is there a step change between the pre-exascale and the exascale machine from that?
It's really hard to say because it depends so heavily on what system you're talking about. If you try to untangle the web of NRE that goes into a DOE system, there's so much cross-fertilization going on that it's really hard to figure it out. The Chinese have a significant amount of NRE going into their systems. Some of the leading-edge systems coming out of the EU, I think, have a lot of NRE. And then you have some of the more traditional users, say a place like the Swiss Supercomputer Center or something that goes on, say, HRLS. They're more looking at kind of commercialized products. So it can span a significant percentage of the ultimate system to basically whatever a vendor's R&D budget was with a little extra added in from the users.
Right. And that's the question that we're trying to put together in this whole framework, is to actually show the whole landscape that Bob's talking about, how much NRE is going in each technology area, storage, interconnect, and so on. We're not there yet.